Okay, so welcome to this presentation about the Swedish Institute of Space Physics in Kiruna, with a particular emphasis also on the science program I belong to, the Solar System Physics and Space Technology. And I end with a bit about my own research. But first, a brief presentation of IRF, the Swedish Institute of Space Physics. So we've been active in Kiruna since 1957, and the main reason we were located in Kiruna was then for the geophysical advantage. We are under the auroral oval, meaning that we can study the aurora, and in 1957 that was one of the best windows to understand the near-Earth space. Aurora in those days was pretty much a mystery, even if there were quite good ideas about what caused them. But it's also a very special place for atmosphere. For example, we can see mother of pearl clouds in the winter, which are beautiful clouds forming in the stratosphere at about 25 kilometers. So we have research studying that as well, and also noctilucent clouds at 85 kilometer altitude, and that's almost the same altitude as the aurora. So by ordinary standards, it's a very thin air at 85 kilometers altitude. You know, at 8 kilometers at Mount Everest, it starts to be difficult to breathe, and 85 kilometers is really almost out into space. But still, clouds can form, and that is because in the summer, this region called the mesopause is the coldest in Earth's atmosphere because of air welling up, and as it rises, it cools. So we can get clouds forming at 85 kilometer altitude, and the aurora, which you see in the picture above, the lower border of that is typically 90 kilometer altitude, so it's about the same. And all these phenomena are much studied by radars, because you can transmit a radar pulse and get echoes back from the atmosphere itself, so giving you information about winds and temperature gradients and such things. So this is an example of what the aurora can look like here. And this is when looking straight up to a corona, it's called. So it can be very dynamic. You can nowadays see very nice pictures of aurora and movies even. If you speed those movies up, they can in one way look even better than the real thing. But a really good auroral display over the whole sky, no photo can capture that. Maybe an IMAX movie or something, I don't know. But that's really an experience. So if you ever get a chance to come to the north, if you haven't been here already, you should do that. Something that facilitates watching the aurora in Kiruna is the IRF app Aurora Alert. It's using our all-sky camera and have an automatic algorithm that when it's a good aurora, it will send you an alert, and then you grab your jacket and run out. The best displays usually last just a few minutes, but sometimes it goes on for hours. So it's of course mostly useful in Kiruna because it allows for aurora over Kiruna, but it still tells you that activity is going on. So it could be useful also in other places. So the Institute is divided into some different programs and activities. So we have 3 research programs, solar, terrestrial, and atmospheric research, mostly here in Kiruna, which then use to a large extent radars and ground-based equipment to study the ionosphere and the upper atmosphere of Earth. We then have the Solar System Physics and Space Technology program I belong to. We study mostly the rest of the solar system, not so much Earth and its environment. So I'll come back to that. But from Mercury to Jupiter, our field at the moment. We also have the Space Plasma Physics group, which is doing both Earth and the rest of the solar system. They are based in Uppsala. And we have something called the Kiruna Atmospheric and Geophysical Observatory, which conducts observatory activities using magnetometers, variometers, all-sky cameras, ionosondes, infrasound microphones, and millimeter wave radiometers. And the magnetometers, I think you know what that is. They measure the magnetic field, direction, and strength. And when currents are flowing in the conducting part of the atmosphere, the ionosphere, you get a magnetic field around that current, you know your physics. And you can see these disturbances on the ground. So disturbances of the magnetic field, that's what we're dealing with. That tells us something about the aurora and what is going on. And one way of seeing that there's something going on and maybe run out to look at the aurora is also the magnetometer. So before digital cameras and coming online, that was how we looked at, oh, maybe it's worthwhile to go out and check for aurora. And both observatory measurements and in particular magnetic fields actually go back to some extent to Anders Celsius, the famous scientist behind our temperature scale. Because he was among the first to realize the worth of long time series that are uninterrupted and well controlled, and he said that he wished previous generations of scientists had left him with good data series instead of unfounded speculation. And we still live by that to some extent. So we have our observatory program whose main thing is to make really good long time series. So not in itself to make science with it, but we need to look at it and use it for science to validate it and be sure that we are measuring the right thing. Variometers, they look at the background noise of the sky, and if there's a lot of ionization in the atmosphere, there's much more absorption, so then you see a decrease in the background sky noise. All-sky camera is quite obvious. You saw some examples of that a moment ago. So they look at the aurora. Ionosondes are kind of a radar. They transmit the radio pulse, and when the electron density in the atmosphere or in the ionosphere matches when the local plasma frequency matches the frequency of transmitted by the radio transmitter, you get a total reflection and you get it back, and then you can measure at what altitude you have that plasma frequency, and if you know the plasma frequency, you know the electron density. That used to be very important for radio communications when they bounced the radio signal off the ionosphere, so that was a military interest. Then the military got better ways of communicating. But nowadays, you once again may want to communicate that way, and even small disturbances of the electron density can give disturbances of the GPS accuracy, so there's a renewed interest in this type of information. But actually, you're very much studying this nowadays with GPS signals, so you measure them on the ground and see small delays and disturbances. I don't know exactly how they do it, but they can get the total electron content along some line, and then they can combine lots of different lines from different satellites and receivers, and they can essentially reconstruct what the electron density in the ionosphere look like. Infrasound microphones, they can be used to study when meteors enter the atmosphere. If they're big enough to cause an explosion or something like that, then you can see it. They can also be used to monitor test ban treaties for nuclear bombs and such things, because they also create strong infrasound, as does earthquakes and other things. But at our institute, the main interest is in for meteors coming in, and because they can also be studied by radars, and there's interesting plasma physics phenomena in the sheath formed around the meteor when it is heated as it hits the atmosphere. And then we have a millimeter wave radiometer, which here is a little bit off because it's used to study ozone, and so it's stratospheric research, but that is very suitable to do at this latitude. So a little list of the ground-based systems we're using. ISSC is a big facility to transmit radar signals. So it's something called incoherent scatter radars. They are very powerful. They need a very strong signal and large antennas because the backscatter signal is very weak. But it can tell you about the ionosphere. It can you can deduce the ion drift velocity, the ion or electron density, the electron temperature, and the ion temperature. So that's quite at different altitudes. Then, so quite good description of the ionosphere. And here in Kiruna, we're now building the next generation of that. So it used to be that these radars had parabolas, radio astronomy standards, which you then physically moved in different directions. Now we have phased array antennas. They electronically steerable very fast. And by combining the beams in different ways, you can then get the three-dimensional pictures you couldn't get before. So the latest of the ISSC incoherent scatter radars is called ISSC 3D. The latest version of our auroral imaging cameras is called ALICE 4D, where ALICE is Aurora Large Imaging System. So ALICE is a system with cameras looking in different directions up towards the aurora, and then you can make a three-dimensional reconstruction. And the newest version, ALICE 4D, where the fourth dimension is time, it then also has a pretty good time resolution, so you can follow the temperature changes in a way we couldn't do with the first generation. We then have some meter cameras and are part of some meter camera network. We have infrasound, as I said before. We're looking at these noctilucent clouds I mentioned, so we have a cloud camera network, and our scientists working with that also have cameras that can go with a balloon. And so you get up above the usual weather clouds and then can look at these noctilucent clouds from different vantage points. Atmospheric radars. So we used to have an atmospheric radar at Esrange, the rocket facility here in Kiruna. It is no longer used. I think it's about something like 20 years old and no longer possible to refurbish, and they have not, at least yet, invested in a new one. We used to have a mobile similar radar in Antarctica, MARA, Movable Atmospheric Radar for Antarctica. So it was at the Vasa station for some years, the Swedish station in Antarctica. Then it was at the Troll year-round station. And then we moved it to an Indian station, Metri. And then we gave it to the Indians because we couldn't afford to keep running it. But they could. So to my knowledge, it's still running. We do have a LiDAR, so that's a radar essentially, but with a laser beam instead of a radio transmitter. And that is used for studies of ozone and these clouds, both noctilucent clouds and mother of pearl clouds. And we're looking at trace gases in the atmosphere, mostly related to ozone. So ozone is not so hot anymore. It was very big, maybe 20, 30 years ago. There were big balloon campaigns studying it. People were worrying about the ozone hole. Now we think that problem is solved. But we keep monitoring it. It's still a very good way of understanding the dynamics of the upper atmosphere. And we do expect some changes to come with climate change. So that would be one way where we could spot changes. Here's a picture of ISSC 3D. So it's a forest of small antennas. That's what the modern radars look like. Not as impressive as these big 30-meter parabolas, but they are impressive in another way, and they are very, very powerful. ISSC 3D is not up and running yet. They have made some test runs, but it's still under construction. This is what the auroral imaging system looks like. It's small hats placed at suitable locations, suitable distance from each other, so they get a good view of the aurora. And this is a bit typical of working with ground-based systems. When you work with spacecraft, your spacecraft go to super cool places. They go to the moon, to Mercury, to Jupiter, everything. When you work with ground-based systems, you can yourself get out in the woods. This is maybe not so exclusive in some forests, some distance from Kiruna. But I will show you in a moment more exotic locations where you can go. But it's also cool to be outside and do things. We had an experiment called Bror, barium release sounding rocket. So a sounding rocket was released from S-range. It released barium, which is a very cool substance. It starts to shine very quickly when there's some sunlight, and then it gets ionized quite quickly, and then it shines in another wavelength. So you can compare the ionized part and the non-ionized part, and that way you can understand the electric field that moves around the charged particles and compare that with the wind that moves around the neutral particles. So that was a really cool experiment, and I was sitting in what is it called? Nikkaluokta, a very dark place with just the right angle towards the barium release to get it from different directions for 3D reconstruction, and we were taking photos with our own cameras. So it's cool to go on such an expedition. Here's also an example of the Transat 2024 balloon being shown. That's the one looking at noctilucent clouds with a set of cameras on board. So this is what the barium release cloud looked like. So the more bluish one, if I remember right, are the ionized ones that move, and here is where you can go really exotic stuff, Antarctica. So when we had this Mara radar in Antarctica, some of us went there, including me. So here's a photo of me setting up a radar in Antarctica. And it was really, really cool to be in Antarctica. I can only say that. I didn't see penguins because I was at this Nunatak in the middle of Antarctica. No, not really in the middle, but away from the coast. But still living in what feels like a Swedish mountain hut, working outside in essentially, well, it was midnight sun, but it feels like Swedish spring winter here in Kiruna. Warm sun, temperatures around 0, very comfortable to be in, and a nice gang. That was really cool. No, I don't remember why I put this picture here, but okay, we leave the ground-based stuff. If you go out in for this solar system research, we know the Earth space environment quite well, and this is a picture of Earth and its magnetic field to scale. So the Earth's magnetic field matters a lot for the near-Earth space environment because magnetic fields affect charged particles, and the space around Earth and in the whole solar system is permeated by charged particles. The solar wind coming from the sun, consisting most of protons, maybe 5% alpha particles, and then smaller and smaller amounts of ever heavier particles and electrons, of course. And those charged particles are strongly affected by the Earth's magnetic field when they come to Earth, and a bubble is formed around the Earth called the Earth's magnetosphere. Similar bubbles are caused around the non-magnetized planets Mars and Venus, which are shown here in red and some greenish color. But because they don't have internal magnetic field, it's only induced magnetic fields from currents induced in their conducting ionosphere. And therefore they become much, much smaller, and this shows this to scale. So we've been looking a lot at what is then the effect of this magnetic field and of the solar wind interaction with the atmosphere. So that's been the idea that the atmosphere of Mars was removed by the solar wind, and you need a magnetic field to protect the atmosphere. We don't quite believe in that anymore. Our research shows that Earth loses just as much particles per per second as Mars and Venus, maybe even more. The magnetic field kind of extracts energy more efficiently from the solar wind because it's bigger. To some extent, it protects, but you get very effective interaction in the polar caps, where we have the aurora and so on. And that outflow is about as big as we get from Mars and Venus. And Venus has a much, much denser atmosphere than Earth. And Venus doesn't have a magnetic field. So we see a problem with that theory. It's still very often mentioned in popular science articles and such things. The main reason Mars lost its atmosphere is probably the gravity is just a bit too weak. There is a dissociative recombination of iron or molecular ions in the upper atmosphere of all planets. But at Mars, the byproducts are above escape velocity. They're not at Venus and Earth. So this is likely an explanation. Magnetic fields could still possibly play a role, maybe with a much, much stronger solar wind, which we believe there was in the past. Maybe it would matter more, but we have been trying to look at escape of atmosphere during storms and such things, and we still have a feeling that no, the magnetic field wouldn't really matter in the end. We get enough protection, so to say, from the induced magnetic fields forming around the non-magnetized planet. But this is the type of science questions we are dealing with. So yeah, this is actually a talk I gave for LTU master students here. So I mentioned if they were interested in mostly ground-based, but it's still for this little audience as well. If you're somehow interested in ground-based research and something, there's the STAR research program at IRF you should contact. But now I leave that and go to the space-based research, some rockets and satellites. IRF was founded in 1957, the year of Sputnik, so that's when the space age started. IRF space age, in some extent, then started in 1968 with the launch of ESRO-1, the one of an European, well, what is now European Space Agency, it was then called ESRO. I think the whole organization was called ESRO, actually. Well, never mind. This first spacecraft where we got to build an instrument to be on board. And that's very important to get a ticket into building more instruments to put on spacecraft, because if you propose to build an instrument for a spacecraft, the first thing they will ask you, what experience do you have in this? How do we know you can do this? And then it's very important to be able to say, well, but we have the knowledge, we have the experience. Then later in 1986 came Viking, Sweden's first satellite at all, but our first research satellite, follow up together with Germany by Freya spacecraft in 1992, which is the year when I started at the Institute. A bit later, we had Astrid 1, 1995. This was a really small spacecraft, not much bigger than an overhead projector, which nobody knows what it is anymore, but they cube something like this. And they named the instrument on it after, they were called Emil and Pippi and such things. And they wrote to Astrid Lindgren and asked if it was okay. And she said, yes, fine, I'm soon up there with them anyway myself. I think she lived several years after that, but anyway, Astrid 2 was a magnetospheric studies spacecraft. And after that, Sweden unfortunately stopped with those. There was an atmospheric Odin, which I think is still alive actually, or still the data is still used. But then they stopped making our own spacecraft to some extent, maybe because it was quite expensive and difficult to do something really new and worth doing with limited funding, but also because of EU rules of how you can. I mean, if you're going to build satellites in Sweden, we want to do it in Sweden if we're paying for it, and EU rules, then you have to get a bid from everyone in Europe, and then it was not so interesting anymore. They're still working on that at the Swedish National Space Agency on how to support Swedish space industry within the EU framework. Next big step was our instrument Astra on Phobos. That was a Soviet mission to Mars and its moon Phobos. And we were invited to build the instrument. So that was our first planetary mission, and very important then for the future to be on ESA planetary mission. And we also built our own nanosatellite before it was really popular with these CubeSats and such things. It was essentially an electron spectrometer with some computer and solar cells bolted on and an antenna sticking out. It was much built by I think students contributed quite a lot to it. And we had our own little base station here in Kiruna to reduce the cost. And we're still, a very large part of what we're doing is building instruments. They are designed and built here in Kiruna. So some of our scientists are experts on building and designing instruments. I'm not that myself. I'm an expert on interpreting the data. But right now I'm leading the building of an instrument for the Comet Interceptor mission. I will come to that. But then other people are the primary experts on the science side, and I have a technical manager among the engineers who's leading the engineers and so on. So this is an example what our instrument bound for Jupiter look like. So they are on the JUICE, the Jupiter Icy Moons Explorer mission. Is on the way to Jupiter now. And Sweden actually leads 2 of 11 packages on that, or 10 or 11, I don't quite remember. And we in Kiruna lead 1 of these packages and have built 2 of the instruments. That's a contribution from Switzerland, Germany, US is a really big package and huge work, but incredibly exciting. These are long-term projects. The spacecraft will reach Jupiter in 2030, and then we may be working with the data for, well, long after I retire the data, but there will be data taking for several years. And I was on a mission proposal for something called a medium-scale mission to study main belt comets, it's called. So comet is my specialty. So it's asteroids which show cometary activity, and it would have been really cool. It was not selected, and not a problem for me personally, because it would have reached the target in 2048, if I remember right. So we're doing that kind of thing for future generations of scientists. Well, maybe we will be alive, but most of us who work with it will be long retired at least. So I was saying a few words about the JUICE mission and the instrument we delivered. And here they are on this picture I'm showing. They are delivered to be installed on the spacecraft. And we've been involved in a number of planetary missions. So of the more recent ones, Venus Express, orbital Venus, 2005 to 2014. Rosetta was launched 2004, but actually arrived at the comet 2014 and orbited for about 2 years, 2016. Cassini, 1997 to 2017. So that was a mission to Saturn. It was our Uppsala group that made the Langmuir probe. Cluster was a constellation of 4 spacecraft flying around Earth. That was my initiation to magnetosphere physics and spacecraft data studies. Well, in addition to the Swedish Freja spacecraft, but where I really did a lot was with Cluster. We also had data on the Chang'e 6, the Chinese mission to the moon, launched May 2024. So they landed on the moon and measured negative ions in a world first thing. of things still going on. We have Mars Express, which is orbiting around Mars in 2003. That's quite amazing, and I can say that our instruments show very little signs of degradation after more than 20 years of operation. That's just amazing. Swarm is a multi-spacecraft mission made by ESA, where we have made some Langley probe, and yes, I think the Langley probe we contributed. It's 3 spacecraft with very precise measurements of the magnetic field of Earth. Magnetospheric multiscale MMS is an American mission. Just amazing how good data they give, how high time resolution, angular resolution, everything they have is really something, a big step forward. Solar Orbiter was an ESA mission to study the sun, and it's still ongoing. And Chang'e 4 is a Chinese mission to the far side of the moon, launched in 2018. So we have an instrument on this Chinese lander sitting on the far side of the moon. The moon is a really harsh environment. It's too hot to do a measurement during day, too cold to make measurement during night. And a day and a night is 1 month. So then at twilight, the instrument wakes up and can do some measurements for some time, and then it goes back into hibernation. What's coming up next really is Bepi-Colombo mission to Mercury. So it's on its way. It will arrive in late this year. And then there will be orbiting, I think orbiting session is late this year, and then they will start the proper measurements next year, really. But we made flybys, so we have some Mercury data already, and the first paper has been published. JUICE, I mentioned, is on the way to Jupiter. It will do some Earth flybys, so we will get some data before we arrive at Jupiter. It's made one. The next one is coming up later this year. Comet Interceptor, the mission I'm leading. I will talk more about that later. Or I'm not leading the mission, I'm leading our participation in that mission. So the instrument we're building for it. Turkish lunar mission is a Turkish mission to the moon. So we will orbit and we will measure something called energetic neutral atoms. So that's essentially the ions that have lost their charge. Ions can get much higher energies than neutral particles. But then when they lose their charge, they are interesting because then they go straight past electric and magnetic field. They're not affected. And studying them is a bit like getting a camera pictures of what's going on. ISRO Venus Orbiter is an Indian mission to Venus. We are building an ENA instrument for that as well. And then on very short notice, we've been involved in Ramses, which is a mission to asteroid Apophis, which is passing close to Earth in April 2029. So essentially, we're taking a German spare instrument from JUICE, and we are building the data processing and data handling for that. So we are involved. And that's, of course, because this asteroid is passing so close to Earth, it's a great chance to study something and see how it interacts with the near-Earth environment. So what's going on right now? I mentioned that Mercury, we are flying past, we made flybys. So this is an example of what some of our data look like from such a flyby. X-axis is time, y-axis is energy of measured particles, and we fly through the magnetosphere, the region dominated by Mercury's magnetosphere, and we see some particles in that magnetosphere. And at Earth, we get trapped particles, radiation belts, ring current particles. So since Mercury's magnetism is very small, it's very dynamic. There's no atmosphere and ionosphere giving inertia to it. The planet takes up a very large part of its own magnetosphere because the magnetic field is quite weak. So everything is very different from Earth. And here we're then trying to understand this whole dynamic environment. Comet Interceptor will go up into waiting orbit, wait for a dynamically new comet. A dynamically new comet is one that has just been perturbed from its orbit out in the Kuiper or Oort cloud and is now coming close to the Sun for the first time. There are leftovers from the formation of the solar system. We would like to see them as pristine as possible because those we have studied before, like with Rosetta, they have been around the Sun several times. They, in some sense, heavily processed. So we're building an instrument that will measure ions. So the round thing here, if you see my cursor, yes. Will measure ions, and then this slit here will measure energetic neutral atoms. So this is a very low weight instrument. Essentially, we're doing as much as we can with 1 kilo and 2 watts or something like that was the limitation. In the end, it weighs a little bit more. One reason is the radiators you see on the side here, which were needed to keep the instrument cool enough, because we will sit on the hot side looking upstream towards the sun. But it's not state-of-the-art in the sense of how good measurements it can do. It's state-of-the-art in how much measurements you can do with a bit over 1 kilo mass and a bit over 2 watt power consumption. Jupiter is then another target, and a very exciting one because it's just more of everything. The radiation belts are tremendous. Radiation environment is a huge challenge. The magnetic field is super strong. All these moons with icy moons with possibly oceans under icy surfaces. One of the moons, Ganymede, even has a magnetic field. And this is a picture. If you could see Jupiter's magnetosphere from Earth, it would be huge, despite the fact that Jupiter is so far away from Earth. Now you can't see it, unfortunately. That would have been cool. And there are 4 very different moons we will, to some extent, study. So Io has 400 volcanoes, main source of plasma in the Jupiter magnetosphere. I mean, how cool is that if you study magnetosphere? And here there's the moon that is the source of not the atmosphere like at Earth or at Mercury, it is the solar wind that is the main source. Europa, we believe there's an ocean under the surface. We could dream that maybe there could be life, not so likely maybe, but still. Ganymede is the one that has its own magnetic field. So a magnetosphere within a magnetosphere. Also, it's subsonic as opposite to the solar wind interaction with planets. So that's a really new thing we can study. And then Callisto, which is incredibly scarred and been through a lot of bombardment and such things. So all cool for many different reasons. So ending up a little bit about our planetary research. So here we mark with a little IRF sign. We've been to Mercury, Venus, Earth, the Moon, Mars, Jupiter, Saturn, and Comet 67P. And actually, we were involved once upon a time in measurements from Halley's Comet 1P as well, but that was much less extent. Yeah, this is for students. We can skip that for you. A bit about my own research. So in recent years, now I can make a short summary. I started out with radar, these ice-cut radars and the ionosphere. Then we combined that with the Freya spacecraft. We was at low altitude, like peaking at 1,700 kilometer Then I moved to the cluster spacecraft studying the Earth's magnetosphere and in particular ion outflow and how the Earth loses some small part of its atmosphere due to interaction with the solar wind. It's not significant. We obviously have an atmosphere left, but it's still interesting to understand these mechanisms because in principle it could be important and it could have been important in the past, both for Earth, Mars and Venus. Then it was decided I would take over responsibility for our participation in the Rosetta project, where we had an instrument called the ion composition analyzer. And the twin of that instrument, almost identical, was on Mars Express studying Mars. So we decided I would start working with that instrument. That would be the best preparation for the comet, because after launch it would take 10 years before we reach the comet. So this is something about how typical ESA mission can go. They decide to go there in 1993. They get actually the idea in 1986 after the Halley encounters and the Giotto mission. But that goes into actually deciding to go forward in 93, start building instruments 1996, launch 2004, and then 10 years in space, including in hibernation when it was so far from the sun that the solar panels couldn't really run the spacecraft, just keep a sleeping computer alive, and that computer essentially had a wake-up alarm, and it started up, and then that automatic algorithm orients the solar panels towards the sun, orients the high-gain antenna towards Earth. And we had an event at the Downstart, ESOC, the European Space Operations Center, I think it's called, so where we control our spacecraft in Europe. And essentially, we were looking at an oscilloscope signal, and it was flat like this, and then you got the carrier signal, and that's, yeah, sure, it's speaking to us. And then we started testing the instruments, and in 2014 we arrived, set down a land in November 2014, and then kept escorting the comet until we passed the sun and went further out again, past perihelion when we were closest to the sun and out. And at some point, we were once again too far out for the solar panels to really work. So the spacecraft got as close to the common nucleus as it could, and then it was essentially a soft crash landing. And we had an event at ESOC again, and this time it was similar. We looked at some carrier signal, and it got flat, and then we knew it was over. We also got the latest images from the camera and all that, how the surface just got closer and closer, and then it's dark. IRF had a Langmuir probe and an ion composition analyzer. I will not say too much about what those instruments do, but Swedish companies built the onboard computer and the high-gain antenna, so we have a pretty good presence. And comets are a very interesting phenomena, very variable, spewing out gas and dust. And I said we arrived in November 2014, and within our team of the Rosetta Plasma Consortium, we had a bet who can first detect the comet in the data as we're getting closer. And you will get a bottle of champagne, those who won. And what I'm showing you here is apparatus is the solar wind with the highest energy blip is the alpha particle, then comes the protons, that was the solar wind looked like at an energy about 1 kilo electron volt. That's how we measure energy in this business. But then down here at 10 electron volts, that water ions just ionized from the comet atmosphere. So the bottle of champagne was ours. Some other teams in retrospect claimed that they could see the comet earlier, but that was not what the bet was about. Who was first sure and totally unambiguous that we're seeing the comet. So that was fun. And Rosetta was kind of walking pace around the comet, 1 meter per second. That's amazingly slow, but it's because the comet gravity is so low. around the planet, the speed of a spacecraft is kilometers per second, a few kilometers per second. Escape velocity from Earth is 11 kilometers per second, so somewhere below that if you're in orbit, somewhere above that if you're making a flyby. And if you're in an orbit, you would typically go out in the solar wind, go back into the magnetosphere, and then you see the changing environment. But at the comet, it was rather the environment that changed around us. So first we were in the solar wind, and then when the comet was so close to the sun that the whole comet environment expanded, then we were inside the comet magnetosphere and then out into the solar wind again, which was a very different way of things happening. So this is just an example that we are still working on the data. So this is my latest paper submitted just before Christmas. I actually got it back the day before Christmas, which was really surprising. You normally wait a few months, and now it took a couple of weeks, and I have unfortunately not returned it yet with revisions I need to make. They're not very big, but I was on Christmas vacation, and then I was on this flurry of things to do because I've been on Christmas vacation, and soon I've just started actually revising it. I think I can skip this maybe, but we are having several master students. We've just had a guest PhD student. We got funding for one new PhD student that we will announce the position, and this concerns Comet group, so my studies. So I can skip that as well. And we're close to 1 hour now, so maybe soon enough. But a few words about the Comet Interceptor mission, because that's my biggest thing now. So that was a proposal by someone called Gareth Jones in UK, and Colin Snodgrass at the University of Edinburgh, and joined also by Italy, Cecilia. And it was selected by the European Space Agency, and we were trying to get on board, saying that we can make an instrument. It weighs nothing, consumes no power, and we were successful in that. And the idea is then to study a comet. And I already said we want to dynamically new if we can find one. So, and finding one, so we launch the spacecraft into waiting orbit and hope we have by that time or during that waiting time we can find a comet. But of course, when it's far out, it's not very active, so it's much more difficult to spot it. But we have the new Vera Rubin Observatory. I think it's active now. You may know more than I about that. But when we started that, it was being built. And so that's a big hope, and they make statistical estimates how likely is it that we find a Christian comet, and it's reasonably high. And if not, there are some backup targets. I still think they're arguing about which one is the best. The challenges are that the relative speed of the comet and our spectrum, it will be a flyby. We will just fly by once. And the relative speed could in principle be more than 70 kilometers per second. An object spewing out dust, which you pass at 70 kilometers per second, that's a little bit difficult, right? And we can't really predict what will be. So there are a number of challenges, and also it's a design to costly mission, they say. So normally, if you design what science you want to do, and then you see what that costs. Here they say, we have this heap of money, how much science can you do with that? But the solutions are, one is we have a limited radio link to Earth as an encounter, so we will store stuff on board and then download it later. And we will have a dust shielding, so a shield with many layers like this. If a dust particle hits one, it will blow a hole in that, and maybe in the next and the next. But they know that pretty well, how to build that. And it will wait at the Lagrange points for a limited time. They say something like 3 years, and they have this backup. And this is what it could look like. The green here is then the orbit for the Lagrange point where we are waiting. Yeah. And then the spot some incoming promising comet. They calculate where would we intersect with that. So it have to be in Earth's orbital plane. There's not enough fuel to go on any exotic trajectories. And then we would launch it so that we intersect it at just the right time and fly by. And it's a multi-spacecraft mission, which is also pretty cool. So one main spacecraft A, and then a B1 built by the Japanese, and a B2 that goes closer, so close that there's a risk that they collide with the dust and are lost. But yeah, no risk, no gain, right? Very unlike ESA to do something like that, actually. They play super safe normally, but interesting way of doing things. It was also interesting to see the whole procedure. So two consortia were bidding to build the spacecraft, and we had to sign non-disclosure agreement. Everything was very secret. There must be no leakage between the two competing teams. I don't think that was a problem in any way. But they chose OHB Italy in the end. And then we will fly by. So I'm working comet data from Rosetta. I have data for 2 years. We can play with the instrument, fine-tune the settings, change a bit how we measure. Here we will, in best case, get maybe 48 hours of data, maybe 1 hour, depending on how fast the flyby is. Maybe 1 hour is really interesting, close to the nucleus. We don't quite know yet. So that feels really odd, however. But it will be interesting to see. There are 2 cameras, one on one of the small. Well, there's actually 2 cameras on all 3 because the Japanese also have a hydrogen imager, but 2 normal cameras, so they can look at the nucleus from different directions and some type of 2D and 3D reconstruction. And this is the team that worked with proposing it, so that's quite a lot of people already there. That was before the mission had even really begun. And what are we doing? So this is what our instrument looked like. So this is a CAD drawing, but the actual is very similar. And then we've considered what we don't know exactly what the environment will be, but we can learn from Comet 1P, Giotto mission, and Comet 67P, etc. So we looked at what we could expect and what the requirement would be. We looked at this energetic neutron atom production, where that could happen. We learned from 67P, and I flew a virtual 67P, so a virtual instrument planned for Comet interceptors through this environment, and noting that yes, we would be able to measure with this to set the requirement. And right now we have built the flight model. So first we build a technology model to test everything, and we have to improve, and we change it a bit, and then when we're happy, we build the flight model. So to the left is the technology model, and here the flight model with the thermal hardware on for a while. Here are earlier stage with all the different parts. Here's an example we're doing a depth test. That's where we mount the physical parts for the sensors, where we will have high voltages. Before we put in all electronics that can be broken if there's a discharge or something like that. We put up just the mechanical parts and apply the high voltages to make sure that works. So there are lots of such tests, and we've had discharges and had to repair small parts and find out how could that happen. But now we're really close. Our delivery of the flight model will be later this spring, end of March, beginning of April. Yes, so that was it for me. Thank you for your attention. Then, a bit about what we're doing here in Kiruna, a bit about the solar system and physics and space technology program, and a bit about what I personally do. Thank you.
Thank you, Hans. It was very interesting. Glad to hear some insights on the IRF. It was very fun.
Yes. Yes, thanks. Yes.
Sus, do you have any questions or are you all good? All clear. Glad to hear. I'm sure will be some people watching afterwards now. Hopefully I can like publish it on YouTube or somewhere where they can watch it.
Okay. Yeah.
If that's fine by you, of course.
Yeah, yeah. Fine.
Well, thank you, Hans. It was very interesting.
Yeah. Thank you, Edwin.
You-
Yeah.
I'll hear from you and your missions again sometime.
Yes, yes. You're most welcome to visit them. You know that. It's a bit far to Kiruna for most people,
Yeah,
unfortunately.
I've been there once. I was at Rymdcampus at a trip to.
Oh,
I was at Nikolauta and then Kebnekaise.
oh, yes.
So
Very,
very fun. Yeah, I was stargazing as well. Um,
yeah.
Maybe I'll come by again. Hopefully, I'll stay
Yeah,
up at LTU, so maybe we'll meet there.
yeah, okay. You're most welcome. Yeah, okay.
Have a good day. Thank you
Have
for
a good
everything.
day. Yep, thank you. Bye.